Okay, gravity and orbits. First of all, we'll start with gravitational field strength. So gravity G, small g, units of which are Newton per kilogram or meters per second squared. You may be asked the question in the exam for 1 mark, multiple choice, or even just to state the units of gravitational field strength or gravity. Newton per kilogram is fine. Meters per second squared, the same as acceleration, is also fine, because gravitational field strength is gravity or acceleration due to gravity. So it is what causes objects to fall and accelerate towards the center of the Earth. Alright? An equation that you're not expected to know and necessarily have seen, but it is in some of the worksheets you can have in GCSE. This is the true relationship between gravitational field strength, mass of the object, capital G is the gravitational constant, and R is the radius of the object, such as the Earth, the Moon, the Sun, anything that has a mass and has gravity. This is the equation you may be expected to use, but it's very unlikely. So you won't have seen this before. All this is saying is gravitational field strength for an object, for example on the Earth, which is 9.81 or 10, which is acceptable at GCSE. That value comes from the fact that the Earth has a mass m. What this equation says is G is directly proportional to m, so the larger the mass of the object, the greater the gravitational field strength should be, i.e. the Earth is much more massive than the Moon, and therefore has a much larger gravitational field strength than the Moon. G is a constant, so G is the universal gravitation constant, which applies to anything in the universe. R the radius. Now, because this is on the denominator, it's also the radius squared. You'd expect the radius to have a larger impact on G than the mass of the object did. So if radius changes a little bit, it's squared, which means it affects G a lot. But if the mass changes slightly, then yes, it will change, it will affect it, but not as much as the squared radius. Because R is on the denominator, it's inversely proportional to G. So the larger the radius of the object, the weaker the gravitational field strength becomes. All that means is, if you're standing on a planet and you're at the surface, G is acting towards the center of that planet. The further away you are from the center, the weaker the gravitational field strength would be. So the larger the radius, the smaller the gravitational field strength. However, the more mass that this planet has, the larger the gravitational field strength will be. So they both have an effect on G in opposite ways. Now, you'd expect R to have a larger impact because it's squared. But the Earth, compared to the Moon, let's say this is the Earth, the Moon would look something like this. So this is the Earth, this is the Moon. We know the Earth has a larger gravitational field strength than the Moon. We have 9.81 Newton per kilogram. The Moon is around 1.6 Newton per kilogram. The Moon has a smaller or lower radius than Earth, therefore G should go up. So if R goes down for the Moon, G should go up as inverse proportion. However, the mass of the Earth is so much bigger than the mass of the Moon that actually that brings us back above. So based on radius alone, the Moon should have a higher G, because smaller radius means larger gravitational field strength. However, the mass of the Earth is so large that it overtakes that effect of radius, and then it brings us back to a 9.81 G. So the mass is actually the contributing factor that makes the Earth have such a larger G than the Moon. But radius of the Moon should increase its gravitational field strength. Questions that can be asked in the exam. Explain why, if the radius of the Moon is smaller, is the gravitational field strength not larger? And the answer, because although radius is inversely proportional to G, the mass of the object is directly proportional, and the mass of the Earth is so much larger than the mass of the Moon that that actually outweighs, if you want, the factor of radius. So our G is much larger than the Moon because our mass drags us and takes us that much further. Alright? So that's that. Weight. If you're standing or anywhere near a planet with its own gravitational field, so it has a gravitational field strength G because it has a mass, then it will apply a force. If you are inside the field, just like an electric field, if you're inside the field of another charged object, in this case, if you are in the field of an object with mass that has a gravitational field strength, then it will apply a force on that object. If you're in the field Your mass, so your current mass in kilograms, call it 100 kilograms. If your mass is 100 kilograms and you're in the field of the Earth's gravitational field, then it will apply a force on you, which would be your mass multiplied by the gravitational field strength. So 100 kilograms times 10 gives you a weight, which is a force of 1,000 newtons. So weight is the force of an object on the object's mass, or due to its mass, and gravitational field strength. Weight equals mass times gravitational field strength. Alright? So that's weight and that's gravity. Orbits around the Earth. So we've already said in the heliocentric model of the solar system, we said the planets, they look circular when we draw them, but we know that they're not quite circular. They're elliptical, they're squash circles, they're more oval. We have artificial satellites orbiting the Earth. There are 4 different types of satellite that we have orbiting the Earth, which takes a different path. We have a circular orbit, which is called a geostationary satellite. Geostationary satellites specifically orbit with the Earth. They're geo, or Earth, stationary. You have to have a geostationary satellite directly above the equator, and it turns every 23 hours, 56 minutes, or 24 hours. Every time the Earth rotates, that satellite rotates with it. It has to be above the equator, and it stays in the same point. The reason that we use geostationary satellites is for broadcasting, television, live TV around the world. We have highly elliptical orbits, much like the comets in the solar system have the highest elliptical orbit. Highly elliptical orbit satellites offer communications near the poles. We've got polar orbits, specifically traveling around the poles and getting to areas, broadcasting and transferring information to areas that the other satellites won't reach. And then a low Earth orbit, which is the lowest, the orbit that orbits lowest in space, basically, closest to the Earth. Alright? And a comment that's made about that and what you need to know is that this low Earth orbit for the satellite orbiting around the Earth, this one requires the least fuel to put it there. So, if you want to take, at the end of the day, if you want to send a rocket, a spacecraft into space, the hardest thing that you have to do that is to overcome the force of gravity that is pulling everything back down. You need fuel to constantly be fighting against the gravity pulling you back. Now, the further you want to go, the more you want to leave the Earth's gravity, the more fuel you're going to require. If you only want to put a satellite in a low Earth orbit, then less fuel is required to overcome the gravity. Alright? However, moving on to this section, when they are in orbit, we're going to assume that they're circular orbits, so we can refer to circular motion. Alright? If we put a satellite in a circular orbit around the Earth and it's close to the Earth, we know that it will have the strongest force of gravity acting on it. Therefore, the velocity of a satellite that's traveling around the Earth has to be faster to overcome that stronger gravity. So this low Earth orbit will be the fastest traveling satellite. If you are traveling close to the Earth, the gravity is stronger, it's going to pull you back to the ground. But if you want to overcome that, you have to travel around in a circle faster. So essentially, if you want to avoid being pulled back, travel faster, and you will make sure you continue traveling in that circle. Okay? We know from circular motion, there is a tangential velocity acting on the object. The velocity of an object traveling in a circle is at a tangent to the circle. Its velocity is constantly changing. Its speed is constant, but its direction constantly changes, so its velocity constantly changes because velocity is a vector. It's at a tangent to the circle. There is also a force acting towards the center of the circle called the centripetal force. You have to have a centripetal force and a tangential velocity in order to be moving in a circle. Now the last thing, we already said a closer satellite to the Earth requires a faster speed in order to overcome the stronger gravity. But if you want to move from one orbit to another, either move to a higher orbit or a lower, the way to do that is to change your speed. If you want to come down, if you're in this high orbit here, and you want to bring this satellite down, all you have to do is slow it down. Because if you slow it down, gravity will take over, it will start pulling it in towards the Earth, Then what you do as it starts falling, so you slow it down, and the way you slow a satellite down is by firing jets out the front. Because if you fire jets out in front of you, it will slow you down that way. Okay? So you apply a force that way on the particles, they apply a force that way according to Newton's third law. This will bring you down. So slowing down the satellite brings it closer, but when you get to the point that you want to be, the new orbit that you want to be in, because you're closer, you have to then travel faster than you were before. Remember, the closer you are, the faster you have to travel. But if you want to move closer from here to here, first you slow down by firing jets forward. That will bring you in because gravity will take over. Then if you want to stay here, you have to increase that speed to higher than it was before so that you can maintain that new lower orbit. And the opposite is true. If I'm in a lower orbit and I want to move further out, then I have to speed up. Because if I want to get away from gravity even more, I need to increase my speed. So to go from low to high orbit, you speed up by firing jets behind you, firing you forward faster, which will take you further out. And then when you reach the new orbit that you want to be in, you have to slow it down to then whatever it was here, it will be slower in a higher orbit because you don't require as much speed to maintain that new higher orbit. Okay? That's it.